The title of this note is Estimating with Finite Sums, and the outcome is that you'll be able to use what is called rectangular approximation method and also the trapezoidal rule in order to estimate the area under a curve. So one of the things that we can now calculate is the distance traveled. So you might remember that distance equals rate times time. And rate in calculus, remember, is a derivative. So the derivative of distance is velocity. So if you take your velocity and you multiply it by your time, that'll tell you the distance that you've traveled. So I'm just going to make a graph here. Let's suppose that the time is along the horizontal axis and the rate is along the vertical axis. And let's say that you went 60, write it down here, 60 meters per second for 4 seconds. So what distance did you travel? If we were to graph your speed, your velocity is constant, 60 meters per second. And you traveled for 4 seconds. So what this makes is a rectangle where the height is 60 unit meters per second and the width is 4 seconds. And to find the area, you would multiply. So 60 meters per second times 4 seconds gives you 240. And what I want you to notice is when you multiply seconds times meters per second, the seconds cancel out and you're left with meters. So that's another hint to you that multiplying will give you the distance because distance is traveled in meters. So you can see this algebraically on the right side, and on the left side you can see this graphically. Now, here in this example, it was really easy to find the area because it made a rectangle. But what happens if we have a velocity that's not constant, something that's not a rectangle? So how do we find the area under a graph that is not a rectangle? Well, we're going to use rectangles. So this is called the rectangular approximation method. So I've got a curve here a couple times, this picture at the top. And there are 3 different ways you can use rectangles to approximate. So the first one is called your left endpoint. It is called your LRAM. The L is for left and RAM is for rectangular approximation method. And so what the LRAM does is we draw a bunch of rectangles under the curve where the left corner of the rectangle touches the curve. You can see that. And what we would do is we would find the area of all of those rectangles and we'd add them up and we would be approximating the area. I hope you can see that we'd be a little under because those rectangles don't quite cover the curve. The other thing we can do is we can come from the right. This one's called RAM. So again, we have a bunch of rectangles, with 4 specifically, and the right top corner touches the curve, and you can see these rectangles are a little bit over the curve. So that one's going to be an over approximation. And then there's a third method where you use the midpoint, MRAM, and so the middle of each rectangle is on the curve. This is a better approximation because a little bit of the rectangle is over, a little bit's under. So not going to be perfect, but we're going to get pretty close to the area. So we're going to do an example here. We're going to estimate the area under the curve, and the function is y equals negative x squared plus 4x. And we're going to look from 0 to 4. So here's the graph of that. And we're going to do this with 4 sub-intervals. That means we're making 4 rectangles. We're going to do all 3 methods. So let's start with LRAM. So we're going to draw 4 rectangles. Each rectangle is going to be a width of 1 unit. And the left side of the rectangle touches the curve. Now the first rectangle is actually a little tricky because the left side's right here, so there is no rectangle there. So we're going to find the area of each of those rectangles, and we're going to add them up, and that'll approximate the area under that curve. So the first rectangle I hope you see is easy. The height is 0. So the first rectangle has an area of 0. The second rectangle has a width of 1, and the height is right here. It's 3 units. The second rectangle also has a width of 1 and a height of 4. I'm just reading that off the graph. The third rectangle, again, a width of 1 and a height of 3. So 0 plus 3 plus 4 plus 3 equals 10. So right now we're approximating that the area of that rectangle is 10. So that's LRAM. Now we're going to look at it again with RRAM. And then we'll do MRAM last. So this one we're going to do RRAM, a right rectangle. So we're going to come from the right side to draw our rectangles. So those are the 4 rectangles where the top right corner touches the curve. So again, the first rectangle has a width of 1, height of 3. Second rectangle is a width of 1, a height of 4. Third rectangle with a width of 1 and a height of 3 again. And the last rectangle has an area of 0. So I can see this one's the same. The plus 0 equals 10. So LRAM and RRAM in this case gave me the same approximation. Now what about MRAM? Let's see if that one gives us the same. So this time our 4 rectangles are going to be centered. So we're going to have the first rectangle right there. The second rectangle will be right there. The third rectangle will be the same as the second one. And then the fourth one. Okay, so the heights aren't quite as easy to tell. It looks like the height of this is 2, but I'm not sure if it touches exactly. So here's how I can confirm the height of that first rectangle. I know that my function is negative x squared and then minus 4x. I just want to check to make sure I copied that correctly. Yeah, it's plus 4x. So negative x squared plus 4x is my function. Okay. Now this midpoint happens when x is 0.5 or 1/2. So the height would be the output of the function at 1/2. So I can solve this algebraically. So the height, it's not actually 2, it is 7/4. So it's a good thing I checked that algebraically. So the first rectangle has a width of 1 and a height of 7/4. Now the second rectangle has the height is the output at 1.5. So again, I'm going to do something similar here. I'm going to do f of 1.5. I'm going to use fractions because they're easier for me to square without a calculator. And then this will be 12 divided by 2, which is 6. I'm thinking of 6 as 24/4, and 24 minus 9 is 15. So the height of that second rectangle is 15/4. So now I'm going to check the third rectangle. So the third rectangle, the midpoint happens when x is 2.5, so f of 2.5. Again, fractions are actually going to help me here just to do this without a calculator. 2.5, that'll be 5/2. So I'm going to do negative 5/2 squared plus 4 times 5/2. So negative 25/4 plus 20 over 2. That's because I'm doing 4 times 5. 20 over 2 is the same thing as 40 over 4. So I picked up the wrong color there. And then 40 minus 25 is 15. So the height of that one is also 15/4. And then the last one, the midpoint happens at 3.5. So f of 3.5. And again, fraction's going to be a lot easier. That's 3.5. That's 3 is 6 over 2, and another half will be 7 over 2. So I have 7 over 2 squared plus 4 times 7 over 2. So squaring both the top and the bottom. And this will be 28 over 2, this part right here. But I really want it in fourths, so I'm going to double 28 to get 56 over 4. And then I see 56 minus 49 is 7. So now I'm going to add up the area of all 4 rectangles. They all have a denominator of 4, so I'm just going to add the numerators. So 15 and 15 is 30. 7 and 7 is 14. So that's 44 over 4, which is a little bit over 10. So the LRAM and the RRAM both gave us an approximation of 10. The MRAM is giving us an approximation a little bit more than 10. So this is pretty imprecise. There's a couple things we can do to make it a little bit more precise. So the last way we're going to approximate is by, instead of using rectangles, we are going to use trapezoids. So the trapezoid you may have seen in geometry might have looked like this. They also could have looked like this. And what we're going to do is we're going to turn these trapezoids on their end. We're going to rotate them so that they look like this. So really what's happening is we're drawing, instead of a rectangle, a series of trapezoids, which are rectangles with triangles on top. And I hope you can see that the trapezoids actually follow the curve much better than the rectangles do. So this is going to be an even better approximation. So how do you find the area of a trapezoid? The area of a trapezoid, actually let me go back and draw the geometry style. The two sides that are parallel are called your bases. They're not the same length, so we're going to call one of them base 1 and base 2. And the distance between them is called the height. And the way you find an area of a trapezoid is it's 1/2 times the sum of the two bases times the height. So on these trapezoids right here in blue, the distance between the two bases is the height. And then the height on one side will be base 1, on the other side will be base 2, and it doesn't matter which one you call base 1 or base 2. So it might help me to think about these heights first. Luckily they're on the curve. So this one has a height of 0, 3, 4, 3, 0. So the first trapezoid has a height of 1, so I'm going to do 1/2 times, and then base 1 is 0, base 2 is 3, and the height, or the distance between two bases, is 1. That's the first trapezoid. Second trapezoid, 1/2, and then the two bases are 3 and 4, and the height between them is 1. Okay, then the third trapezoid, 1/2 times the sum of the two bases, and the height between them, which is 1. And then the last trapezoid, 1/2 times the sum of the two bases again, times the height, which is 1. Notice how all of these are multiplied by 1/2. It's actually GCF. So a lot of people will just take out the 1/2, and then they'll do the sum of the two bases times the height. It's really convenient here that the height is 1. It's not always going to be 1. So I'm rewriting it just to give you an idea of what you would have to do in any situation. All right, so let's add these up. 0 plus 3, let me move that out of the way. 0 plus 3 is 3, times 1, still 3. 3 plus 4 is 7, times 1. 4 plus 3 is 7, times 1. 3 plus 0 is 3, times 1. 1/2. So 3 plus 7 is 10. 7 plus 3 is 10, so that's 20. And half of 20 is 10. So the trapezoidal approximation gives me 10 again. So those are your 4 different methods for estimating the area under a curve. And that'll be the end of these notes.